So the unitarity theorem. So for applications in physics, it's important that the matrices representing our groups be unitary, okay? So why is that? The reason is because of quantum mechanics. So in quantum mechanics, suppose you make a transformation to a system, and the transformation is represented by some group element in some group. So for example, it could be a rotation. So you take a system and you rotate it, right? That would be a transformation. Or you can take a subsystem, suppose like an electron, which is interacting with lots of other electrons, and you can choose to rotate part of that system, right? Or you can say, okay, I'm going to take the whole system and translate it in space. That's another transformation you can do, which is represented by a group. Or you can take part of a system and apply this translation on, say, one of that part, right? But the idea is that there is some group element associated with that transformation. Now, according to the postulates of quantum mechanics, this transformation is represented, and here we use a group theoretic term, represented by a unitary transformation. By a unitary transformation on the part of the Hilbert space which represents the transformed part of the system. Okay, so it could be that if you take the whole of the system and say do a transformation on the whole system, then we make the transformation on the whole Hilbert space. So if H is the Hilbert space of the whole system, and suppose psi ket is a vector in that Hilbert space, then your transformation G, which is a transformation you make on the physical system, will induce some unitary transformation on psi. Okay, so if you apply, say, G on the system, then your state of the whole system will go from being psi to U G of psi. Okay. But if, on the other hand, your Hilbert space is, say, part of two particles, you have two particles, say particle 1 and particle 2, then your Hilbert space is a product, say, of these two particles, and there could be entanglement and stuff like that. And suppose you just make a transformation on the first one, for the second one, you don't do anything, then what will happen is that you have to, your psi 1, the part of the states which live in the first Hilbert space, you know, that one will be transformed by a corresponding unitary transformation. Whereas the second one, you know, the part of the state which comes from H2, that guy won't change. And it's important because if, you know, if, say, you know, this is a symmetry, if these, you know, transformations are symmetries, so for example, if you have a time-independent Hamiltonian, then time translating it will not change the energy. So if these transformations are symmetries, then, you know, this thing, the inner products, will have to remain invariant. And if, so we are assuming that when you transform the system, you know, the states transform like so, then of course the inner product will remain invariant you know, this will remain invariant if U dagger of G is U of G is 1. That is, if U is a unitary matrix. And this is why we want in quantum mechanics the representations to be unitary transformations, okay? So this is motivation. Do you understand that? For physicists, this should be a well-known fact, but for mathematicians, this is for the benefit of the mathematicians. So we haven't really talked about the theorem yet. So the theorem is as follows, and I don't think I'll be able to prove it today, but I want to give you the statement and state a lemma which we will need for the theorem. And so all finite groups, and by extension, all compact Lie groups admit finite dimensional representations which are unitary or unitary representations. Finite dimensional unitary representations. So what do I mean by that? What I mean is that the matrices representing you know, these groups must be unitary matrices. Okay? So before we move on to prove this theorem, which will take a while, so that's why I won't go into that today. Let me just remind you of a result that you were supposed to prove in one of the assignments. And we will be using this, this lemma. And the lemma is that if you have, if G is a finite group, so it's a finite discrete group, then if you have any function of the group elements, and if you sum over all the group elements, then that sum is equivalent to the sum over that function where the group element has been right multiplied by a given group element G tilde, or left multiplied by a group element G tilde. Okay, do you remember this?
Yes, sir.
Okay, this was pretty easy to show. I hope it was. So this can be generalized for compact groups, and I'm not going to give you the proof. And the idea is that for compact Lie groups, what you can do is that you can, the sum over all the group elements can be replaced by a very nice convergent sum called the Haar measure. So it's an integration measure, and this measure is known as the Haar measure. I don't know if you guys have done any measure theory, but this is something that is covered in the measure theory. Okay, so then what happens is that the integral of the Haar measure with f of g, this is equal to g d of mu of g f gg prime, or f of g prime g. Okay, so this is the continuous version for compact Lie groups of this result. Okay, so this is basically what helps us prove the theorem that we will prove next time for compact Lie groups. Okay, I think that's all I have time for. Before I take the attendance, can I have some questions? So I mean, we'll talk about explicit representations very soon of groups. This is a bit abstract. We won't be in abstract land for too much longer, maybe another lecture, and then we'll talk about very, very specific representations of very specific groups. Okay?
I have a question.
Yeah.
I missed what S was in the explanation of reducible representation.
Right. S is a similarity transformation. Like, that, when you have S is some matrix, which is not dependent on G. If it exists, if S exists such that, the representation can be put into this form. Okay. Why is this? Because we know that, matrices and linear, so if you have a block diagonal matrix, right? So if I give you a block diagonal matrix, say D is a block diagonal matrix, right, like this, right? So I can take some arbitrary, some random matrix, say B, so this is a M by N. So this is M cross M, and say this is N cross N. So D is M cross N, so M plus N, sorry, M plus N cross M plus N. Now, if I have some other matrix, say F, and it's some random matrix that you just cook up, right? So if I then, so suppose it's invertible, I say F inverse D of F. So I get a new matrix D tilde. The thing is that the eigenvalues of this matrix and the eigenvalues of this matrix are real, are the same, right? Because if I take the determinant of this guy and this guy is going to cancel out. And the trace of this matrix and the trace of this matrix is also the same, using the simplicity of the trace. So morally speaking, the matrix D tilde and the matrix D are the same. So you might be given a matrix which superficially doesn't look like it's a reducible representation. Then it's your job to find out whether or not it's a reducible representation. And there are algorithms for doing that. But once you have found the reducible representation, there's a matrix which will give you, by similarity transformation, take you to the diagonal, the block diagonal matrix, right? And that matrix is going to be the similarity transformation, the S matrix. Okay?
Yeah, understood.
I mean, you know this because, you know, if you have some matrix and you have to block, if you're asked to block diagonalize it, what you have to do is that you have to find the eigenvalues essentially, right? And once you find the eigenvectors, you know, all the eigenvectors themselves may, you know, they will make some matrix. And that matrix is going to be S, and that matrix is going to give you the diagonal matrix, right? So S is that particular matrix.